about this cumulative distribution function. It tells you what's the probability that your random variable is involved some number. Now, I want to talk about this in which we do know that seeing a person who is, well, maybe not exactly 175 centimeters, but about 175 centimeters is much, much more likely than seeing somebody who is 230 centimeters. Unfortunately, this function, the cumulative distribution function, doesn't show you this information. So, on the one side, it's more or less meaningless asking what's the probability of seeing somebody who is exactly 175 centimeters. That's meaningless because, well, a measurement will give you not exactly 175, but 175 point something, and basically the probability of getting exactly 175.00000 is quite close to zero, or exactly zero. But on the other hand, we do want to compare the probability of seeing somebody which is approximately 175 centimeters with the probability of seeing somebody who is approximately 230 centimeters. So we do want to compare which events are more likely, more frequent, which events are less likely, less frequent. And for this cumulative distribution function is not really a good thing. We will talk about instead about what's called probability density function. So first the intuition. Let's say I want to quantify how likely it is to see somebody who is approximately 175 centimeters tall. So I'll talk about the probability of somebody being approximately 175 centimeters. So let me say from 175 to 176. It is some number. It captures some information about how likely it is to see somebody who is about 175 centimeters tall. It can be easily expressed in terms of this cumulative distribution function. We just discussed what it is. It is F176 minus F175. But then it's not quite what I want. It tells me something about this actual range from 175 to 176. What if I don't want anyone 175.5 centimeters and lower? What if I want just really, really close to 175 centimeters? So, then you might suggest doing something like this. Compute this probability instead. If I want the measurement to be precise up to half a centimeter, maybe this is a better measure. Well, it's quite likely that this number will be about twice as small as this number. Because the people here, in this range, well, approximately half of them will be from 175 to 175.5. The other half will be from 175.5 to 176. So this number is going to be twice as small. Approximately twice as small. So, to remedy this, I will divide this number by 2, or rather divide by 0.5. This will put these numbers on the same scale. Now they measure the same thing. How likely it is to see somebody who is about 175 centimeters tall, except this one makes a measurement which is, you have a tool which shows you roughly centimeters. This measurement shows you the answer using the tool which measures half a centimeter. We'll keep using more and more tools. So measure the height up to 1 millimeter. number is going to be approximately 10 times as small as this one. So to normalize, I will multiply by 10, multiply by 0.1. So in general, what I will want to do, so this is just discussion before the lecture will finish. Now comes the lecture definition. The probability density function at the point x is defined as follows. It's the limit as delta x goes to 0 of the probability that the variable is from x to x plus delta x. So just this thing is always 0. So if you look at the proportion of events which are from x, the x plus really small margin, it becomes smaller and smaller, this margin becomes smaller and smaller. But this thing, after normalization, like we did here, becomes a meaningful number. So this thing measures in a way how likely you are to see somebody who is, or how likely you are to see the variable in about having value about x. In terms of this cumulative distribution function, we know this. So we know that its limit is delta x equals to 0. This thing is f capital F x plus delta x minus capital F x divided by delta x. And if you recall from the previous course, this is a familiar operation. It's just the derivative of capital F. So this thing measuring how likely it is to see that the variable is about a given value happens to be the derivative of the cumulative distribution function. And quite often it's convenient to work not with the cumulative distribution function, but rather with this function, probability density function. Before we actually start talking about this probability density function, let's write down some quantities. Maybe let's make a connection between the density function and the probability and the cumulative distribution function. Properties. Now f is going to be the density function, capital F is going to be the cumulative distribution function. So first property, the density is the derivative of the cumulative distribution function. That's just definition. Less obvious, if you know this probability density function, can you answer such questions? What is the probability of your random variable being between one number and another number? So, what is the probability of your random variable being between A and B? Well, in terms of cumulative distribution function, it's just capital F of B minus capital F of A. But now recall that small f is just the derivative of this capital F. So this thing is in fact the integral from A to B of the density function. That's fundamental theory of powers. If you know that capital F is the derivative of small f, then this integral is this difference. So this tells you that the probability of seeing the variable take a value between a and b is just the area under the graph of density function from a to b. Another property. What if you want to reconstruct your cumulative distribution function from the density? Well, this is the probability of x being the most x by definition. Well, what is it? It's the probability of x being smaller than x and larger than some really large negative number. So it is the integral from minus infinity to x. I don't want to use x again inside the integration, so I'll write f of t dt. So this thing, I'll write here justification for this. So this is the formula, it's important, and justification will come here. So it's the limit of probability of x being the most x and at least a as a goes to negative infinity. So as you capture more and more events, you get closer and closer to this thing. The probability of just the variable being smaller than x. And this is the limit as a goes to negative infinity, integral from a to x of t dt. And we call the integral by this name, integral from minus infinity to x of t dt. So there is a way to go back and forth between the one function and another one. Small f is derivative of capital F is the integral from minus infinity to x of t dt. So other properties, well, capital F is increasing. The corresponding property about the density is the density is always positive, not negative. Because derivative increasing function is positive. So capital F is between 1 and 0. This doesn't have simple interpretation. Limit of f of x as x goes to infinity is equal to 1. This has a simple analog in terms of this density function. What is this limit as x goes to infinity? It's the integral from minus infinity, and you make the upper one go plus infinity. So overall area from minus infinity to infinity under the graph of the density function is 1. So in a way, that's an analog of saying that the overall probability of getting some outcome is 1. Okay, and this property doesn't have a simple. So these are the things that you should remember about the cumulative distribution function and the density function. It is in a way easier to work with the density function case, visually. It's easier to work with the density function rather than with a cumulative distribution function. Just look at, say, this example. just by looking at the graph, I see what are the more likely outcomes, what are the less likely outcomes. I see that if I keep repeating my experiment, I will get much larger cluster of outcomes near 5 than near -5. Because this area is much larger than this area. I see that kind of most of this area is concentrated somewhere here. So most of the outcomes should fall in this interval. I see from this that kind of outcomes which are larger than 10 are more or less symmetrical with outcomes which are smaller than 0. So it shows that you are likely to get more or less as many outcomes larger than 10 and as outcomes smaller than 0. So by just looking at this function, you see quite a lot about the variable, about the random variable. Let's solve an exercise about this density function. Zero x is negative, and c times e to the power minus 2x, and this is positive. So sum c and x is time in dx. Equations are y and c. Second equation find the probability and the server will be functional after 3 years. So in this case, the event is just for extending the server and waiting until it fails. Whatever you measure is the time until you actually see it fails. The density function for this random variable happens to be of this form. So somebody told you that, well, after thinking hard, we arrived at the conclusion that the density function looks somewhat like this. We don't really know what it is seen, but overall the shape of the density function is like this. So it's not relevant to the measurement. Let me draw a graph of this function. So it is 0. And it is negative, which is reasonable So you see that most of the probability is concentrated somewhere in the beginning. So the server is more likely to fail right away than after you wait for a long time, which is reasonable. Well, that's the density function. Okay, so how to find this constant C? Let's answer the first question. So we know that not every function can be a density function for a random variable. A density function must satisfy some properties. What properties? Well, if it must be positive, that's fine. If C must be positive, and that's not enough information about C. The one which is relevant is this one. Overall probability of something happening is 1. So integral under integral of the function on the whole real line must be equal to 1. So use this step. So this will have to have pretty simple. A function is defined by two different expressions depending on whether x is negative or positive. So split this integral two parts. Integral from minus infinity to 0 of 0 dx. Because my function is 0 from negative infinity to 0. Plus the integral from 0 to infinity of c into minus 2x dx. So first integral is just 0. Integral of 0 is 0, no matter what the limits are. Second one is more interesting. So it's the limit some large number goes to infinity, integral from 0 to this large number, c goes out, e to minus 2x dx. And the antiderivative of this is defined. C times e to minus 2x minus 2 from 0 to n. So here I basically just guessed it. I know the derivative of minus 2x is minus 2 times e to minus 2x. I don't know the minus 2, so I will write this. And then a lot of this because minus 2 is just a constant. And finally, we find the limit. So when n is really large, e to the power minus 2m, or minus 2m is large and negative, e to this power is close to 0, e to large negative number is close to 0. So this limit is 0 minus the value of this is at 0, which is c times 1 divided by 2. So it's 0. On the other hand, this integral is 1. Once again, because it is a density function. Yeah. Okay. So C must be 2. That's the answer. Once again, if you know the function, almost know the function, but you have a parameter in this function, to find this parameter, you just know the overall area of the graph-based function, the overall probability must be equal to 1. Questions about this computation? Alright. Let's find the probability that the serval will be functional after 2 years. So what is it in terms of this density function? question of this kind. I want to find the probability that my variable is, in this case, larger than 3, smaller or equal than, well, nothing, infinity. So this integral, this probability should be the integral of my function from 3 all the way to infinity. So I don't want to restrict the upper f. So here it is the integral of my function from 3 to infinity. Because for positive x, my function is just 2 e to the power minus 2x dx. I can write this integral in this way, and then continue. So maybe I will skip the calculation. Turns out to be e to minus 6, which is approximately approximately 0.0025. Or if you want better understanding of probabilities, I mean more intuitive understanding, you can write it as 1 over 400, which will mean that if you repeat this experiment 400 times, only one time out of this 100, you should expect your server to last more than 3 years. So questions about this. So here the essential point was just this actually understanding that the question is equivalent to completing the integral of the density function, integral of the density function from 3 to infinity. Okay, so now we know how to answer simple questions like what is the probability of a variable moving from A to B using either the cumulative density function, cumulative distribution function, or the density function. Now I want to talk about expected value of a variable. So if you keep repeating this experiment over and over and over, on average, how much will be calculated until the cell clears? Reasonable question. So what is the expected value of this variable? Start thinking how to approach this question. How to approach the question of what is the expected value of a variable. Well, for a discrete variable, for a variable with finitely many outcomes, it was, well, we just took the outcome itself, multiplied by the probability of getting this outcome, and then we've taken this out. In this case, we have a continuous variable. There are infinitely many outcomes. You can't just take a sum. But we can write something like this. So, let's say that we don't really measure the variable precisely, but we use the measurement tool with an error of delta x. So we round every outcome to the closest kind of delta x. Then we get something which is a discrete variable. Something with, well, not finitely many, but with outcomes which are separated from each other. And then we can take a sum. So if we are using a tool then we can do the following. The expected value is going to be more or less, well, I'm writing more or less because we are measuring with an error. But then it's going to be the following. If the sum of outcome x times the probability of this outcome. But the probability of this outcome is basically the probability of getting an answer from x to x plus delta x. So delta x is just, I think about some small number. So if I measure height, I think about maybe 1 millimeter or 1 centimeter. So instead of measuring the height precisely, I will say that every time I measure the height, I will round to the closest centimeter. And then what I will do is, to find the expected value, I will take the sum of all measurements, so all the numbers, let's say all the integers from 100 to 200, centimeters, and then I'll multiply by the probability of getting this measure. What is it? It's the probability of getting the variable between x and x plus delta x. And the sum is for all possible rounded, all possible outcomes is rounded up to delta x. But then what is it? We know what is this probability. My definition of the density function is the density function evaluated at x multiplied by delta x. Once again, approximate. So we know that this thing is capital F of x plus delta x minus capital X, which is approximately the density times delta x. And then multiply by x. So overall, it's the sum of x, f of x, delta x. Now to make this measurement not approximate but rather precise.
Is there any way you can write that little writing figure? Just to the yeah.
Yes. So it's the probability of my variable in x. So to make this more precise, I'll make delta x smaller and smaller. So I'll subdivide my whole interval to smaller and smaller subintervals. And I'll make the roundings to be more precise. In the limit, I know that this thing is exactly a Riemann. It's a Riemann sum for the whole integral. Well, I'm taking the sum over all possible values of x, so it's the integral from minus infinity to infinity of the function x, f of x, dx. So this part was just an iteration. This thing is the definition which you should either understand or remember. So basically it tells in the summation, which is this integral. Integral is basically a fancy way of word for infinite sum. So it's the sum of the outcome multiplied with probability, which is basically the density function. So that's the expected value over here. Once again, it's good if you understand this thing, but you must remember this thing. So you must remember the definition of expected value. And the inclusive mean is once again the same. It's over many trials. What is the average of your error? So as an example, in this stable server, which one was continuous, what do we expect that this server will last? So what is the expected value of So I'm talking about this function. Now I do know that this number is 2. So I'm talking once again about this example, but now my question is, what is the expected value of my variable? Expected value of x is by definition this integral. Integral from minus infinity to infinity of x into minus 2x, sorry, 2 into minus 2x, oh, sorry, x times f of x dx. So by definition, the expected value is just integral of x at x dx. In this case, my function is well, defined by different expressions for negative x and positive x. So split the integral into two parts. Integral from minus infinity to 0, x times 0 dx, plus integral from 0 to infinity of 7, x times 2 into minus 2x. First integral is 0 because I'm integrating 0. Second integral is the limit as m goes to infinity, integral from 0 to m, x times 2 e minus 2x dx. So now you see that this is an integral which we know how to compute. So integral of x times e to minus 2x, so can be computed using part A as a partial integration by parts. And the answer is 1/2. So I will do computation because I don't know more things. But this integral can be computed, then this limit can be computed, the answer is 1/2. So what this tells you is, if you take a whole bunch of identical servers like this, and you measure the times to failure for this whole bunch of servers, and then you take the average outcome, the average outcome is going to be close to 1/2. In approximately 1/2 year, you should expect on average. Okay, so questions about density function, remote function, expected value. Not half the times, no. So my variable is the time to failure in years. So if expected value of this variable is 1/2, it means that the average time to failure is 1/2. It means that if you take 1,000 servers, for each one you wait and record the number So similarly to the case of discrete variable, we have the notion of variance and standard deviation. And it's basically the same thing. Probability times S minus average squared, and then sum. So probability f of x times S minus average squared, and then the sum, which in this case becomes mu is equal to rho of x. And the standard deviation is as before square root of variance. And typical features of say low variance and high variance. So typical feature of density function where variable with a low variance is something like this. So most of the area is concentrated around the edge. So in this case, the variance is very low. High variance is either like this. So you can expect maybe different outcomes roughly around the average, but they are actually spread out. Or maybe something more discrete like this. And then different outcomes, the average outcome is somewhere here, but the actual outcome that we get are far from the average. So let's the intuitive meaning of variance. It captures somehow how spread out the outcomes are around the average. And basically, finding the variance and standard deviation is just finding the. I want to mention one extremely important distribution, extremely important density function, which is called normal distribution. And it's so important because it appears almost everywhere. I'll explain exactly what condition it appears. Normal distribution. So today I'll probably just start talking about it and then use half an hour on Monday to finish talking about it. Okay, so normal distribution. That's a distribution with the following, that's a variable with the following density. 1 over square root of 2 pi sigma e to the power minus x minus mu squared divided by 2 sigma squared. So it is such a variable, so it's variable with going to be like this. It's what's called Gaussian bell curve. The largest point of this curve is x equal to nu. So it looks something like this. The largest concentration of probability is around the mean, and then as you go further and further, it becomes really, really small. And it actually becomes really, really small. So if you go 2 or 3 standard deviations from the mean, it becomes almost zero. And first of all, why it's important? So it turns out that if a random variable actually happens to be kind of the result of averaging multiple factors, then basically it's going to be distributed like this. For example, height is basically produced as a result of averaging the influence of many, many genes. So height is distributed in this way. And if you fix the gender, and the height of the gender is distributed by color. Similarly about lots of space. Similarly about random numbers. So they are usually distributed around the image of the exact number, and then there is some errors. Maybe one important thing, last important thing to know about this normal distribution is the standard deviation. So for a variable which is normally distributed around the mean, you have the following